poster presentation. I invite Dr. Noha Khamis from Warwick University, UK, for her poster presentation.
Okay. So can everyone see my screen?
Yes.
Okay. So I am Noha Khamis from Warwick University, and I will give like a talk about it's not a talk, it's a poster about one of my project in PhD. It's
Can
about.
you please enlarge it a little more?
Sorry?
Can you please enlarge it a little more, if
Okay.
possible?
Yeah. This is okay?
Yeah, it's fine.
Okay. So I'm gonna speak about the effects of heterocycle sulfonyl group on enzymatic selectivity and reactivity of Noyori-Ikariya catalyst in asymmetric ketone reduction. So I'm just like, I will explain more about what is a Noyori-Ikariya catalyst. So it's like a kind of half sandwich complexes. It's a class of half sandwich complexes which contain ruthenium metal with a wire ring and like chiral ligand like the dipene or something like this. So like how this catalyst induce enantioselectivity for for a polar compound or polar bond like ketone. So it's like this kind of catalyst is operated by through two interaction: attractive electrostatic interaction where the allyl ring of the ketone will get interact with the allyl of the catalyst, and will be attractive electrostatic interaction. While for the opposite side, if this allyl ring, if the the alkyl group or aryl group from the ketone get like the opposite side, will be a little bit repulsion between the electron density of aryl ketone and the lone pair of sulfonyl dioxide, so SO2 group. Okay, so like if the ketone get interact with this way, will give like 97%. But like if there is also high chance this will be occurred unfavorable interaction between bi interaction and lone pair, so it will give like around 3%. So the difference between them give like EE, which is represents an enantioselectivity for this catalyst. So why the chiral alcohol? This will lead us like using this catalyst will give us like a way to synthesis chiral alcohol, which is quite important in building blocks for many drugs. So this study will focus on changing, like it's common for the Noyori-Ikariya catalyst, especially Noyori version, to be the sulfonyl SO2, it will be attached with a ring. So let's try like in this study different heterocycle sulfonyl group and see if this will like improve the reactivity and enantioselectivity of this catalyst or not. So the focus of this study just changing the group of heterocycle sulfonyl group. So in the beginning, like ligand already synthesized using the reported method and like reacted with the source of like ruthenium complex. It will be like usually dimer, and it's a quite quick reaction. Just in triethylamine and IBA, just 1 hour, you will get your complex. And by this way, we already like synthesize 6 complexes. And we to check the configuration, especially for this catalyst, this kind of catalyst, you should check the configuration of the complexes. So like X-ray is already obtained, and this is the X-ray for the complex number 5, and this is the X-ray for the complex number 4. Here, like there is a quite interesting thing happen. Like here, like in the quinoline ring, it's like a self-reduction was happened during the reduction. Like during the synthesis of the catalyst, a self-reduction already happened, and like tetrahydroquinone is already formed. And we can see here, like in the X-ray structure, like a hydrogen bond will be formed between NH and ruthenium. And this will make the structure quite stable. And it changes the configuration. Like usually the expected configuration to be SSR or RRS. But in this case, we got SSS, which is quite unusual for this class of catalysts anyway. So like testing this catalyst in ketone reduction, like simple ketone, like acetophenone, and do some NMR conversion to see like the conversion rate, the reduction rate with the time. It was observed that like the catalyst with furan ring, it was quicker than Noyori catalyst. It's already doubled the rate. But for the tetrahydroquinone, which is number 4, it's reduced. And this makes sense because like maybe because this of the hydrogen bond is quite stable, the structure, so it will make the activation of this kind of catalyst is quite hard. So by this observation, we testing this like after we already screen this using NMR. We tested in different substrate, simple ketones like acetophenone, parachloroacetophenone, orthochloroacetophenone, and it was found that we got already a good improvement where we can see here like this kind of catalyst, like especially with heterocycle group, like quite reduce the also compound, also substituted acetophenone compound, much better with high EE, much better than Noyori-Ikariya catalyst. Like we can see here, like for example, catalyst 5, like here reduce or 2-methoxy acetophenone, and we got around 97% EE as our configuration. And so in the conclusion, we succeed to make 6 complexes and tested and characterized it well and tested in a wide range of substrate. And we found also these catalysts like show a potent selectivity for all tested substrate, especially also substituted acetophenone. And some of them were faster than in reduction than Noyori catalyst without effect on enantioselectivity. So yeah, thank you for listening to me. And I would show thanks to my supervisor and my funding. Yeah, thank you.
Thank you, Noha. It was great to listen to you. Any questions?